Good afternoon, everybody. Thank you for joining us to our pollution prevention webinar series. Now, today's webinar is like energy saving strategy. Today's webinar is webinar industrial energy management, how much you can save. Actually, it's like in April 9, 2026, and it's coming from the Center for Sustainable Energy and Environmental Engineering. Dr. Cardenas, can you go to the next slide, please? Our mission here in the Center for Sustainable Energy and Environmental Engineering is provide scholarly and applied research and consultancy for sustainable energy development, conservation of natural resources, and also the center strives to enhance public awareness, promote renewable energy technology and natural resources through a focus on research and workforce training. Next slide, please. Our services, a lot of you knows what we already been doing for the pollution prevention side, include monthly webinars, workshops, and technical training courses, energy, water, and lean assessments, technical and engineering support, and we also can offer like a cash flow and market analysis for our customers. Can you go to the next slide, please? Some of the webinar details and participation guidelines. The recording will be available after the meeting, and it will be like post in our YouTube channel. For the speaker presentations, will be sent via email after the session. And for asking questions, you can drop your questions in the chat or turn on your microphones, or leave your questions in the Q&A question and answer session at the end. And we always ask you for your feedback. We value your input, so please share feedback to help us to improve for the future events. Next slide, please. Our presenter today is Dr. Cristian Cardenas-Lailhacar from the University of Florida. It's a faculty in the Department of Mechanical and Aerospace Engineering at the University of Florida. He is also the Assistant Director of both the Industrial Training and Assessment Center and the Mobile Energy Laboratory. He works in industrial energy management and productivity, energy efficiency and optimization, policy, new energy sources and materials, chemical reactivity and molecular structure optimizations. And he joined University of Florida in 2003, worked for the Chilean Minister of Energy and for the Ecuadorian government. He rejoined then to University of Florida in 2016. In his work, he has performed over 400 energy audits to industries in Latin America and in the US, including NASA. He is a life member of the Association of Energy Engineers since 2008 and was inducted a legend in energy. Dr. Cardenas has over 50 publications written, 3 books, and 5 chapters in books of energy. So thank you for joining us, Dr. Cardenas, and let's start with your presentation. Oh, Dr. Cardenas, I think you are muted, so.
That might be an important issue. Well, thank you again, Pablo, for your presentation and kind invitation to participate. Today, I would like to transmit to you some of the things that I do through this webinar on industrial energy management. How much can you save? And before I go forward, it's a pleasure to be here, and I appreciate the kind invitation from ECU, East Carolina University, the College of Engineering, Dr. Tarek Abdel Salam, Dr. Marley Irby, and Paulo Nunez Hernandez. And I learned he's from Quito, a country that I visited many times and become to love. And also my appreciation to my colleague, Dr. Sharif, on the Mechanical and Aerospace Engineering Department here at the University of Florida, and to the students of the UF Industrial Training and Assessment Center, with whom we have performed some of the audits which results I'm going to show you, and the experience part of that is also related to this. So let's get started. Here's my outline. I would like to talk to you a little bit about energy use to give some context to our presentation, and talk about why it's so important that we talk about energy and energy efficiency. So to see it as a development metric, and is it or is it not? And you will see the ideas behind that. Then some policy and infrastructure. So what is the relation between these two, as well as when you do policy, what is the behavior within countries, industries, states, companies? So we'll look into that. Industrial energy management, we will talk about competitiveness and innovation, which is what it is, and how much can you save scenarios. So here comes the the main focus of this presentation, and then talk about some innovation and ideas. And then I would like to discuss some ideas on AI and Internet of Things in industry, which is part of AI, particularly in the case of, for example, wastewater treatment plants. And then I will move to net zero for 2050. All this topic has been so much discussions about it, and can we really achieve net zero for 2050? That's going to be the main focus in here. And then talk about how we get there, the baseline and emissions reduction, and how we can help industry to achieve its part into that. And we'll see that some of that will depend on a carbon market, maybe a new one. So let me get started just by showing you with this slide how's the energy being used in the United States. So you see that the blue color is industrial energy usage, transportation, the brown, green, the residential, and the yellow, the commercial. So why like this? Because these are the main 4 sectors that use energy in the country. And for that, they are classified like that for all the countries in the world. So in terms of percentage, in terms of quadrillion BTUs of thermal units. So that is in the period from 1950 to 2024. So you see that we're going up. Not much in the industrial, but on the rest, yes, we are. So energy consumption here is considered to be the electrical systems and some process. And all the information I'll show you comes from or most of it is from the Energy Information Administration. So here we have the sources in terms of fuel, sources for generate power. For example, where is it that they go or generate some electricity and power that, for example, the transportation. So some of all the potential or all the sources of fuel that we have go to the same 4 sources, sectors: transportation, industry, residential and commercial, etc. So in a way, if we group them, they are kind of show you a 3/3. So the US can be represented as a 3/3, except for the fact that we have a good chunk of energy consumption by the electric power sector. So that is of the essence. Now, how is this distributed around the country? Well, here in this graph, you see that just looking at the states on the horizontal axis, you see that the one that uses the most energy consumption in terawatt hour is the state of Texas. The state of Florida is kind of on the middle down, but we still use a lot of energy. And these sources that are being used are shown on the top. It might be a little bit hard for you to see, but what is the relation between the energy usage and this idea of development? What I mentioned before, that is exactly energy is in a way a metric for development. So let's take a look. From the Organization for Economic and Commercial Development countries, you see that there is a relation between the gross development product and the energy usage. And in general, in non-OECD countries that do not follow those ideas and policies, then you see that the energy and the GDP go intertwined. They just go together. When one goes up, the other one goes up. When one goes down, the other one goes down. So they are coupled. The idea or the goal from the OECD or for OECD countries is that these two are decoupled. Essentially, we should continue growing with a better GDP and keep the energy usage pretty much constant. So do more with less or with the same. And that's the main idea. Now, very nicely said, but there are some issues. For example, you might have some problems if you don't expand your energy consumption. For example, this plot here represents power of installed power to generate and the time and the access, the horizontal axis on time. So you might have a state that we have seen in some beautiful state in this country that has constant power installed, no move, no building more power generation possibilities. So if you consider that the orange little line here shows how industry and the country itself is requiring more power, then you will find out that at time 1, there's going to be an intersection of these two curves right here. And if we don't have the power, we don't raise this ceiling, then we'll have shortage of power. And some consequences of that is that some people will not have power in their houses, or to live, or to manufacture any products or provide any services. On the other hand, if we consider that we do energy efficiency and follow some guidelines in general, then for energy policy and energy management, now the country, the state, the industry will behave like the one represented by the yellow line. And it will intersect perhaps this installed power or capacity at a given value, represented by the horizontal line again, but in a further time t2, that will allow us to create more power generation opportunities, possibilities. If we consider cogeneration, for example, it would take 2 years to build a plant of 18, 20, 25, 50 megawatts. So this is a borrowing time, it's a buying of time doing energy efficiency, and to decide also not only do I use fossil fuels, or maybe I use renewables, but times to make decisions on how that is going to help us. Now, if we do this, are the policies to be the same all over the country? If we consider as a world, all over the world, all over the states, all over the industries, all over the plants that a company might have? Yes, no? Well, let me show you this plot here. We show you different states: Washington, California, Texas, Minnesota, Pennsylvania, Georgia. Even if they have the same energy users, as we said before, transportation, industry, commercial, and residential, not all the states use the same fraction of energy for the energy user sectors. Consequently, the policies cannot be the same. Therefore, now let's find out how are we doing in the United States? Well, the United States is doing pretty good on that end, because we see that the total energy consumption is down here, the total, and then the real GDP follows the green line. So there is a decoupling. We are decoupled. Fantastic, because we can continue developing our industry and our society without consuming much more energy. And that's the goal. Now, in terms of policy and infrastructure, how do we achieve that? Well, the goals are to provide adaptation, to provide some mitigation, and do some sustainable development. So not one time and then we forget about it. No, it has to be sustainable in time. It will continue there in time. And then, of course, what that will carry on with is more production, more development, and we have to watch out for the climate change. We like it or not, there's a lot of controversy about that. You might think of yes or no, but still is there, and we can certainly talk about that. What effect will that have? Is a maximum development, comparative advantages to others, or compared to others, so will allow us to do more commerce. We'll be in a much better position to exchange goods and do commerce. And then it will require to have also attached with that some policies and agreements, incentives, and financial aid that can be provided in order to provide better goods or more goods and be competitive and provide those same goods at a cheaper price. So we'll see how that comes. And for that, we will require, again, energy policy. Now, all this what I'm telling you about, the policy and infrastructure, please remember, it obeys to countries, states, companies, industry, local plants, your house, everybody, in a way, if you prefer. But they all have the same structure and have the same consequences. In terms of the energy policy that I will describe later on in more detail, we will ensure to provide security on energy and energy quality, energy as a development engine, provide energy access for everybody, and some energy that is environmentally friendly. That's why renewables are of the essence, and the technology that we have to do with that. So research in here is absolutely needed. Now, what are the institutions that we need to have, or we should have, and many countries don't? A Department of Energy, International Energy Agency, an Association of Energy Engineers, International Association of Economic Engineers, or Energy Engineers. All these possibilities are important. All these institutions are important. Why? Because of this. as countries, states, industries, we have objectives. As for year 20 and for 2050, we will have some objectives to reduce some energy consumption and reduce pollution and make a better footprint, lower CO2 emissions. How do we do that? Essentially, using non-conventional renewable energy sources, energy efficiency, and CO2 avoidance. They will generate more jobs for sure. More jobs, 2 to 5 times more jobs that the same $1 million can generate by the same use of these resources. Now, what about industry? Well, in industrial energy management, the goal is if you can do some research, apply it to your company, to your state, to your situation, then if you're going to be generating policy or being responsible for policy, it allows you to be more competitive. And that's the goal. Competitive because if you can reduce your production costs, those reduction of costs that in general are fixed costs, now you translate it into variable costs. And you translate those variable costs to reduce your cost of manufacturing, and then you translate or you pass those savings to your customers, providing the same goods and the same quality of goods at a lower price. You are more competitive than those that don't do that. And consequently, it's good to increase all that and through innovation. So in industry, there is no energy or regulation rules. There is in the environment on how much you can emit, but EPA is there. They know very well about that, but we don't in industry in terms of energy. So it is important that in industry we consider energy management systems. Why? Because we can save a lot of money, be more competitive, and you have better trade in the market for your papers, if you know what I mean. And then you provide better services. You are also more competitive, and you increase your sales. All these under an environmental impact, social responsibility, ISOs that allow you to be certified, and you are certified if you want to put your products somewhere in the world, Europe, Asia, they will require some certifications that are international, like are the ISOs. ISO 50001 is the certification for energy management. And then you become more sustainable. So all these are good. All these are things that we should be doing and implementing. And they are essentially based on the same ideas. Actually, on ideas. Ideas is what we are supposed to be looking for. Now, let's narrow down our analysis to how is the energy being used. If we look at the state of Florida, with a total of about 220.7 terawatt hour of energy a year, these are in industry the main energy users. Motors and pumps about 50, as always. Air conditioning and chillers 15, lighting 10, air compressors about 15, and then it's the others. But what is interesting is that motors are 50% of the energy use in industry. So if we come up with a policy on reducing the energy of motors and pumps, by say 10%, then we are reducing the energy consumed by the state of Florida by 5%. Consequently, the effect that a policy will have on those particular targeted pieces of equipment and particular type of industry, or all the industry, are great. They are very powerful. Now, how do we do all this? Well, you first have to establish some energy goals. What are those goals? You determine. Some companies will say every year for the next 5 years we will reduce our energy consumption by 2-3%, and that's perfectly fine. That's a goal. Or we will get certified ISO 50001. Perfectly fine. Another decision. But to get to those energy goals, there's a ladder to climb shown by this arrow. And the first step in that ladder is an energy audit. You have to know where you are, how much energy you're using, who is using the energy, what can you do. So this energy audit has as essence, on the essence is a diagnostic. It will check your benchmarking by some analysis, analyze your energy bills, use of non-conventional renewable energy sources, sustainability, and baseline and metrics. The baseline is how the company is behaving in terms of energy usage compared to how much you manufacture. After that is the implementation. Now you have to implement the ideas on the diagnostic. So do you conserve all that, the energy efficiency of the operation, energy management system, and again, non-conventional renewable energy sources, and self-generation opportunities like photovoltaics, thermal energy storage, cogeneration, etc., to say a couple. Then you have to go for measurement and verification. Why? Because to know if what was implemented is, and get some metrics, is it really saving the energy that they say they would save? What about greenhouse gases emissions reduction? Do you have any possibilities for carbon bonds? We'll talk about that in a minute. And what are the economic variables that you are to consider? Also, we'll discuss that. Are there any regulations, that is in the case of emissions, not in the case of energy? And what are the trade effects? Do you have some opportunities in there? Well, as you do all that, and in manufacturing in particular, industry, you have to train your team. The team, I mean the workers that are in the production line, training in the sense that they can take decisions and make decisions as the process goes on, avoiding the fact that many of them have to wait for the plant engineer of that shift where they are to say, yes, you can do this, or no, don't do it. Or they have to be trained to do that. That saves you not only time, but resources. And then it will conform with you an energy team. You have to have an energy team. Why you have to have an energy team? To make those policies that will help you to achieve those goals, to provide incentives, training, energy efficiency team, and energy goals. These have social implications and a commitment. And these are the things that we should be doing in industry. And then guess what? This is the plan. The plan. Then it's you check, and you act with policy and do it again. So this is the plan, do, check, and act. So it's quality control in a way. Now let's take a look on how about competitiveness and innovation, which is now we are approaching to what the main focus of this webinar is. When we have our energy users, again, the main sectors, industry, transportation, mining, commercial, public, and residential, we have a company that somewhere is generating power, which is transmitted through power lines and then is distributed through the substations to the users. But we have to remember, if we want to do some savings, that on the actual greenhouse gases emissions reduction, it's more than just saving 1 kilowatt hour. Let me show you what I mean by this. If you're going to save 1 kilowatt hour of energy, the local power generation plant has to generate 3 or equivalent to 3 kilowatt hour in order to bring you the 1 kilowatt hour. And that's the amount of CO2 that you will be saving. This is one we will use shortly. The amount of the emissions factors for the utility companies in the state. Now, what are the opportunities for industry, states, the country? Well, this table here shows you 4 scenarios on pessimistic situations and optimistic ones. And here you see on the side the actions and expected results. This table here is based on my experience on over 400 energy audits in the United States and Latin America, as was said in the nice introduction by Paulo, is what you have. On the first scenario, and we'll discuss this in a little more detail shortly. In the first case, which is the business as usual, this is everybody goes to work at 7:30 a.m. and you start working, and something happened over there. Your maintenance crew goes fix it and keeps on going just like that. No real planning on being proactive. So it's just reactive actions. Something happened, we fix it, but we don't go to the source and to try to fix it ahead of the game. Savings can be between 0 and 5%. Second scenario, no investment costs, you can save between 5 and 15. You take the average, it means 10%. That might have no need of cost. So the payback, let me put it this way, is immediate. And when we talk about payback, we say simple payback, implementation cost divided by cost savings, that is about 0. So no investment. Why? Because there are some of these that don't require investment. And I'll show you some of that, which are, for example, insulation replacement, repair air leaks, compressed air systems, and reduction of pressure, light up, circular economy, for example. Then we have a third scenario where you have to apply policies and projections. And the range of savings pessimistic is 15 to 30%. Then you have to have some investment, but it's a low cost investment such that the payback, or the simple payback, is below 2 years. I'll show you some examples of that. And the final scenario is a more proactive one, really proactive. These two last, the third and the fourth, are proactive. Not that the number two is not, but much more in terms of resources that have to be invested. So you have a between 30 and 50%, so average 40%. These are more aggressive. Now here you really have to make some investment. And the simple payback is about 5 years. Which are those? Combined heat and power. Combined cycle heat and power, like the natural gas cycle and the vapor or steam cycle, photovoltaic, solar heaters, thermal energy storage, HVAC, etc. When you have to install big pieces of equipment. Now, all these are interesting ideas, and they all reduce energy and emissions, because once you reduce your energy consumption, you reduce emissions. So let me take you to all these other scenarios 2, 3, and 4, except number 1, because number 1 is no action there. So you're not, companies are not proactive into that. So let me take you to this scenario where the simple payback is about 0. Second scenario. Consider air compressors. I'm going to try to go fast here because for the sake of time, so we have enough time to talk about all the rest. Consider that you have a 100 HP compressor, nothing unusual in industry, that runs 3,000 hours, very little, and you generate pressure at 120 psi, but you realize that you need 90 in the process. So you realize, hey, what if I reduce the pressure from 120 to 100, leaving 10 psi on the lines for feeding the air leaks, right? So according to a study by Oak Ridge National Lab, you can say for every single psi that you reduce on the compressed air pressure, the pressure generated by the compressors, you can reduce 0.5% of the energy used by the compressed air system. As a consequence, and if we assume that the load factor, the electric load, is equal to the efficiency of the, just for the sake of the example, then you realize that you save that much energy that provides you this much cost savings. If we consider 5 cents per kWh, which is really low, then you reduce some energy, some CO2. If we consider this value of 0.5322 tons per CO2 per each 1,000 kWhs, and that's it. Now, what do you need to do that? I mean, what is it that you need to do to achieve these savings? Well, I'm saying here that the payback is immediate. Why? Because the only thing you, the operator, and your team on the maintenance have to do is to go to the compressor's control panel and go to the buttons that says reduce pressure or increase pressure. You start reducing 120, 119, etc., etc. You keep on going until you get to 102, 101, boom, 100. How much cost does that imply? Exactly. For those of you that says 0, yes, it's 0. So 0 divided by any number is still 0. There you go. So that's an example of simple payback on the first case, which means 10% with very minor costs. And I have other examples later on if I can. I'll show you. Let's go to scenario number 3, and where you have between 15 and 30% savings with simple paybacks that are below 2 years. Typical LED lights. We all have experience with LED lights. The case here is 20 lamps with 400 watts metal halides that have a big ballast factor, but you replace them with LEDs 110 watts. If you do that change, and if the cost of each bulb is 223.36 cents per bulb, here's your demand reduction calculation, including the ballast factors, 1 for LED. You save 7 kW. If you multiply by the number of hours that these LEDs run, which is 8760, you get energy savings right here. Then the cost savings is going to be the demand and the energy. The demand is its cost, 12 months a year, plus the energy saved times the cost of the energy. Total 3,570. Because you reduce some energy, You multiply by the emissions factor, and you get 32.63 tons of CO2 per year reduced. The simple payback is going to be the 20 bulbs at $223. That's your implementation cost. Divided by the savings, you get 1.27 years payback. Return on investment, pretty high, almost 80%, as you can see. That's scenario number 2. Another scenario number 2, high efficiency motor. I'm going to go a little bit faster just for the sake of time, but consider that you will replace all old motors in the sense that if a motor will fail or fails and you have them identified, you have to have the money in your pocket in order to replace it. So one of the things that in industry is done is rewinding the motor. But instead of rewinding, we recommend you to purchase a new higher efficiency motor, whose cost is going to be in the premium about 30% of the cost of rewinding. So it's pretty cheap because you have to have that money. So you consider here the premium only. And because of that, then the cost savings will be about $2,891 for a motor of 50 HPs, whose efficiency is 78% now, is the old pretty motor of the company. And you replace it with a new unit of 95% efficiency. You run the calculations, you realize you save $2,891 because you save some energy, the 47,950 kilowatt hour a year. You save some 25.52 tons of CO2 per year to emit. And again, the cost of the efficiency motor minus the cost of rewind, the premium, as we just mentioned, divided by the cost savings is 0.42 years. Return on investment, way too high. What do we use or you can use these tools in the Department of Energy toolbox on website, and we have used the measure tool, but we prefer to run it our own, and we have devised our own little calculator tools for our own little software for this and many other ideas. So that's for the motors. What about the environment, the HVAC possibilities? In many facilities like this, it's pretty hot. Some ventilation is installed here, but for heating, these big fans that are called the high volume, low speed fans or HVLS fans provide a column, as it shows in this figure here, a column by rotating of about 8 feet tall, and they do it in a kind of horizontal way, so it's 360. That provides a reduction in temperature on the floor of between 5 and 15 degrees Fahrenheit, so it's pretty good. So what are the savings here? Well, the savings are that if you reduce the amount of the temperature in the plant, in the literature, it says that your productivity in plants can increase for about 2% for every degree Fahrenheit. So it decreases, but then you can take it as you increase it. So the cost savings are going to be the productivity increase minus the energy usage by the HVLS that you use. So the productivity increases, let's say you have 5 workers, you pay $20 a worker. The timing included in there, you save $18,200. The energy use, the electric energy used for the fans is the demand plus the energy. So at the end, you save 3.51 kilowatts, 27,200 kilowatt hour. Multiply these two values by the cost times 12 for the demand, you save about $1,600. Not that much, but you save some tons as well, some tons of CO2. What are the cost savings? 16,000. Well, the implementation cost is $1,250. So the payback is $12,500 divided by 16,587, give you 0.75 years of saving. Fantastic. I will put it in for sure. And that's the feeling that we get from the industry when we talk about this. Or besides that, just put an air handling unit and provide with ducts made out of fabric some more additional opportunities. Another opportunity for savings in the same category of below 2 years is, for example, install turbulators in your boilers. Turbulators, as you see here, this figure represents a boiler, and here you see the pipes. You put these flanges inside the pipes inside the boiler, when you do maintenance or when your team does maintenance, then you put it in there, and these are the savings that you're going to get. So, for example, if we consider 20,000 MMBTU per year of natural gas used to provide heating, whose efficiency is 78%, by installing these turbulars, you can reduce your energy consumption for about 1 to 2%. But anyways, the difference is going to be on the efficiency achievement. So you will improve from 78% to 83%, 5%, according to DOE and these websites that you see here. That means a savings of 1,205 practically MMBTUs. You multiply this savings by the cost of natural gas, you get $2,000. Implementation costs, $200 per flange. $15, 250 flanges is what you need because of the pipes of the boiler. You multiply by the cost of the flange, you get 3,500. The total savings are here. The implementation cost savings are here. And excuse me, 3,750 is the implementation, 2,420 is the cost savings. You get 1.55 years of payback. So the payback is pretty good. Now, let's jump into the fourth scenario, which means bigger investment. And please consider that there's about 120, 150 of these recommendations that appears constantly in industry for energy savings and buildings, etc. So I know we're going to go for a few, but they all fall into these categories, scenarios that I have shown you. Let's consider this combined heat and power system. And consider that for the sake of the example, that we need to satisfy a thermal load of about 27,327 MBDs. Thermal load that can be for heating water for a building, the sterilization area of a hospital, or the laundry of a hospital, for example, or a thermal load that you need to satisfy in an industry. So this diagram represents a turbine. And from the turbine, you inject some fuel and air. Some of the energy will be lost, about 25%, but 35% of that can be converted into power using a generator. And because of the number of hours that you're going to be running this CHP unit, you can get some kWhs. I'll give you a numerical example in a minute. From the exhaust of the turbine, you will get about 40% of the energy from the fuel that you can satisfy a thermal load through cooling or through heating. If it's heating, 80% of the efficiency of a boiler, for example, or COP, you can consider if you have a chiller and you satisfy a thermal load. So with the case that you see here, we can run the calculations on how the fuel is the amount of fuel needed according to satisfy this thermal load, which is this amount of this fraction of the fuel, the energy of the fuel that is coming out, times the efficiency of the boiler. Here you go, you divide it by the thermal load to be satisfied, you get your fuel. From the fuel, you can calculate the amount that is needed and used by the turbine to produce electricity. And from there, you go back and divide it by the electricity, and you get that the size of the turbine is a 1 megawatt. You have some losses because you have the fuel, you multiply by a quarter of that, and you go by 0.25%, and you get the losses. So summarizing, we have a fuel injected to a turbine, you have some losses, but then you generate power by using a generator, a 1 megawatt in this particular case. And if you run it 8760 all year long, which is recommendable, so you don't lose money, you get 8,760,000 kWhs a year to be used. And this is conservative because nowadays this can be 40%, and on the exhaust it's about 45%, and the losses are between 10 and 15%. So let's say about 12%. Then we connect this heat, that is this energy that is coming from the fuel, as heat flow. This is a heat flow diagram. Is here. You put it into a boiler, and you connect it to get it to a boiler, heat water, provide steam, and satisfy the thermal load that initially we wanted to satisfy. So that is what we have calculated an energy savings. We have calculated needed power in order to go ahead and generate or satisfy that thermal load. Or conversely, by satisfying this thermal load, what size of a turbine do I need to do it? So cogeneration has all those beauties, and there's the combined cycle of the gas, this is gas, but also is the vapor. Beautiful technology. It has a lot of potential, and it has always had. So the economics for CHP, on the cost savings, the demand that you will not pay for anymore to the utility company, you become independent. That's the KW, the KWHs per year that you're not going to pay anymore. You're generating them for yourself and using them. You have to discount the fuel and the maintenance. If you were using a boiler before to satisfy the thermal load, fantastic. So now this value will disappear because it will satisfy the generation of power. And of course, the maintenance. Maintenance is very expensive. It's about 1.2 cents per kWh. So you put all the values that you have from there according to what we calculated, the demand by the cost of demand times 12, plus the energy saved times the cost of energy, minus the fuel, and minus the maintenance cost that is there, standard according to DOE and Oak Ridge National Lab. You get all your costs. Your cost savings are $302,404. Notice that in this particular case, even if we are generating power and electricity and energy, you will not have CO2 savings or avoidance. Why? Because it's practically the same energy and power to be generated. Some of the simple payback that you can have is the implementation cost divided by cost saving. I'm going to exaggerate a little for a $1.4 million per megawatt. And the cost savings 302 that we just calculated here, that gives you a payback of 4.63 years, but it could be less. How? Let me return back here to the dial. What about the fuel? By the way, these cost savings are very sensible to the cost of energy and the cost of demand and the cost of fuel. So these are ballpark numbers. Don't take it literally, but please do consider that. Now, in terms of the things that you can do, if you have an industry where you have some biomass, for example, well, this biomass can have the opportunity to be used as a fuel. For example, the skin of peanuts, the skin of rice, etc. Any biomass that you can generate. Even in wastewater treatment plants, the biogas that can be generated, you can refine it and use it as the fuel. Then in that particular case, the fuel is free. So this allows you to have a much better payback, reducing it sometimes to 3.5 years. And even if you consider makers, then you have a better opportunity. This is the maintenance cost according to Environmental Protection Agency, and the $1.4 million cost was taken from US DOE. Another opportunity in the same range is the installation of variable frequency drives. So I'm going to skip this real quick, just to show you that yes, they exist, and the calculations are there. You can save money. The amount of CO2 that you can avoid or save is interesting, 14.68, and the payback is still 2.17. So these are the units that you can install in your facility, and variable frequency drives would allow you to save. That the utility company will see the peak when you turn on the equipment, the peak goes up and then stabilizes to work the equipment. Then you avoid that peak and the equipment will come up to working regime real fast, but real easily, and the utility company will not charge you for the extra that you used. In the thermal area, for example, consider heat recovery for a boiler. Boilers usually get, if this, you allow me the picture, please. If you have a boiler here and you're injecting fuel as well as air, the air that is usually injected into the burning chamber of the boiler is ambient temperature fuel with the corresponding humidity. What we propose, or what we do, is to say we're going to put in this stack over here that has a higher temperature, sometimes 300 degrees, 318, as you see here in the bottom picture, taken with an infrared camera. We put a concentric cylinder, which is a heat exchanger, and by forcing the air to be sucked in, going in a counterflow fashion from how the heat goes out, then the cold air gets warmed up and gets heated and is put into the flame, saving energy. How? By now, the combustion of the fuel represented by this methane, which is the natural gas, we put oxygen and then generate CO2 plus water plus energy. Well, this air represented by oxygen here needs to go to temperature. And the only way to do that is through energy. Who puts the energy? The fuel. Consequently, you're saving fuel. And here is some details of the same. I don't want to distract you with the equations, but here they are. It depends essentially on the heat transfer efficiency of the system that we install. Let me just run over this real quick, but show you a summary of the same that we have done. Here are the ideas that I presented to you. Again, some only. The potential savings, implementation cost, the simple payback, return on investment, energy savings in kilowatt hour, and in this italics is MMBTUs, demand savings, and CO2 reduction. We have organized them in terms of Pareto style, like the more savings on the top, and then you go down. But please note the average of the payback, which is pretty high, but it's not that bad. It's because this is a lot of energy and cost included in there. But we are saving some energy. Now, notice that in this particular case, because of the cogen, we are assuming that you're going to buy new gas. So we are not considering that you are using already a boiler. So then you have to buy some gas. Still, the payback is 4.63. So it's not the optimal case scenario, but it's there. Now I would like to show you some ideas that can go to the use of the new, some new optimization ways for industry. So AI and machine learning. Machine learning, AI is a way of machine learning, if you want, on both sides, but AI and machine learning can learn how to solve problems. They can learn how to make decisions. So AI will enable our computers to that typically require some human intelligence by doing things by themselves. So, and I do that because I say this because we are going to talk about net zero in a few minutes, and I will see how that goes. So let me show you this little video here. This is an AI for a driving car lesson. We have some neural network and some some network, and these are cars that have some generations, and they are learning how to drive, and they have some variables represented here by these lines that are changing. And the reason for doing that is that they learn that this variable makes me hit the wall. I don't want to hit the wall. I need to learn how to go around the circuit and complete it. And I can do that from the first generation, but then for the second generation, etc. So it's a genetic algorithm, if you want, to do the same thing. Now, they finally learn, and him and all the generation that comes behind the sons, let me put it that way, learn how to do it as well. And the goal is to see who are the 10 first to cross the finish line completely in one cycle. So here is what you see now in more detail from the whole system. Now, note that the reason for me to show you this is that because of this, we can use these genetic algorithms to optimize the energy being used in a manufacturing facility. So baseline, equipment list, and energy balance, those are the ideas that we want to pursue here. So after this, after they have learning here, we can show, for example, how much is it that they learn and how they learn and how much they take them or took them, excuse me, to learn this process. And here is that detail. The generations, which are 20, how much it took them to train, how many frames you have, how many active cars, what was the best distance, what was the time, what's the mutation, the population, 400 cars, for example. But after that, let me now show you what is the neural network. Here are the variables, the same lines that you saw from the car, that are changing in time as they change the weight that they have, in order to steer and to accelerate, in order to complete the circuit. So here is how the network is moving, and they are hidden besides, but you can see how they change, making the decision in order to achieve the goal, which is to cross the finish line at the end. And here, finally, we have this curve that talks about the generations of cars, of students that learn, or kids. And what is their score? And you see that at the very beginning, it takes them some generations to learn. But then all of a sudden, between 5 and the 8th generation, the jump is quantic. So they really learn. And then they continue learning little by little, but then they plateau. And that's the main idea of this example. Now, AI into industry, let me just show it to you, IoT into SCADA in wastewater treatment plants. And for that sake, in any chemical plant, they have these systems in where they collect data. The data is coming to the facility, to the plant, and they have this recording and where the operators can change variables and find out what in the world is going on with whatever are the systems that they are controlling. So they can see trends, etc. So it's very interesting. So what happens? The equipment readings provide some information to the SCADA, as you saw on the previous screen. Then you design an IoT, which is a software, essentially, that tells, hey, according to your needs, here are the optimum values that you should be using in your process. And it feeds it back to the SCADA system, and the SCADA applies it, use them according to the operator decisions, and you keep on going. The interesting thing is that with this system, you can use and have the same information in your smartphone, in your tables, in your app. So if the plant manager is in vacation anywhere, let's say comes to Disney in Orlando, or goes to Europe with the family, or goes to the Grand Canyon, he can see that and address issues. So SCADA is one of the systems that go to IoT platform, which is secluded, not all the time, but there are some security issues there. But all these ideas come into the possibilities of use web and mobile applications for analyzing your system. Are there differences between SCADA and IoT? Yes. One is wireless, the other one is not. There is on the premises, the other one is cloud-based. There's strong interaction in IoT across vendors, so to decide what is that you want to do. How many recommendations can you consider here? Here are 21 of them, all AI related to towards IoT in chemical industries. According to the Department of Energy, here are the savings. According to the SWIFT program results that they have. The average energy intensity, it's 1.987. We have 3.7. In the state of Florida, this is our lab results. Then you have the average kWhs per mg, 3,000. The total energy reduction, 6.9. We have achieved 6.48. So we are very much in the ballpark. Now, notice that in the state of Florida, there's about 4,500 plus wastewater treatment plants. So one of the goals why this is not better is because some facilities do not treat the wastewater treatment plant. So that actually they do not treat the biogas generated to transform it into energy. Now let me go to the idea of the net zero. So one of the main issues with these ideas is that there is no incentive really to make those high paybacks better. So since there is okay, oh well, it doesn't want to show up. Let me see if I can. I don't see the pie chart probably. Oh, unfortunately, well, this orange is electricity, this is residential and commercial, industry, and then this is transportation. Those are the energy use. But in the case of the wastewater treatment plants, here is 7 facilities that we audited, and you see that the energy is being used in that in this format, but it's not homogeneous the amount of CO2 that can be saved from or that is generated from them. Here is the energy being used in terms of CO2 emissions. If you're a wastewater treatment plant, these 3 are your major energy users: the motors, the pumps, and the blowers. And we're writing a paper in terms of replacing blowers with another system that is really interesting. One of the things that is interesting is to draw this baseline line, which relates the amount of product that you manufacture in your facility or production in your state against energy usage for your country. And you get a linear regression, and this is how it's done. And the interesting thing is that the in wastewater treatment plant is millions of gallons. The millions of gallons, this slope tells you the energy, total energy used to treat 1 mg. And the intercept is energy used without manufacturing purposes. We're trading water. That is equipment that remains idle, that is just spinning, compressors that are just keep on running, or pumps that are just running, screws that are continue running, but they don't produce any benefit to the plant. The regression is pretty low, 1.98%, let's say 2%. But this is a picture. It might not be pretty, but you know the ideas that behind this, that you can do some things to these might be outliers, but in these particular cases, sometimes they are not. So all depends on the case. In order to see what will be the effect on cost and energy savings and paybacks for carbon credits, since we're talking about carbon credits, how can we make the simple payback smaller, so to make it more interesting for industry, for the state, for the industry, for the companies? Consider these groups of facilities, and we have some reduction on CO2 and some cost savings. Currently, this is what we have. And this is what we have of implementation cost. The simple payback could be 3.17 if we add the current price or cost of carbon credits at large amounts, $6, short amounts, $2, then this is the new payback from 3.17 to 3.15. So essentially, it's no effect. No, why should I reduce CO2? No incentive. So the same happened with the return on investment. And again, the other cases are the same. So today, adding carbon credits to the cost savings has practically no impact in the bottom line of any company and industry in any state. So what we propose, and we have been writing a couple of papers about that, is that since there is no impact, the current market works for the cap and trade, works like you have some energy savings through renewables, you use some CO2, you can offset some carbon with that. And since the market is voluntary, we believe that the best way will be to move from a voluntary market to a new trading market. For those of you who are as old as I am, you might remember that in 2008, former President George Bush, the son, he didn't sign the Kyoto Agreement for a very simple reason. He will put and jeopardize the local industry, but he created its own agreement here in the United States, and you could see in the papers that you could sell carbon credits inside. Nowadays, the costs are so low that they don't make a dent. Then when you have this new market, then you can sell and buy and have a compliance market and go to the cap and trade. But it has to be some regulatory policy that goes about that. Now, not for the sake of punishing, because if you are emitting pollution, you have a boiler or a furnace, you have to have EPA allowing you to emit this much. If you pass it, you will get penalized, but you can go less. But instead of penalizing, if you avoid emissions, we should have a kind of a rewarding system, and that will be the idea that we would like to propose. So unfortunately, I have to say the market today has some restrictions. And one of them is that you have to be certified. Somebody has to certify your emissions. But you can verify it through clean development mechanisms. Projects must reduce emissions, but they only for CO2 avoidance. But the project, as of today, is not, you have to show that it's not for energy efficiency, productivity increase, etc. How come? So you can't apply. So the project is not for profit. Again, how come? Profit from planting fruit trees, for example, is a fantastic idea if you're not going to profit from the fruit. I don't know any packing of fruits company that will agree with that. So there are better chances for clean development mechanism and the idea of using circular economy, of course, but solar panels have zero emissions. Good to implement that to reduce carbon credits or to reduce carbon emissions, but good only if they are 100% sold. The renewables projects must show additionality, so it's in top of, not to provide some instead of, some energy instead of. So the reduction of electricity doing energy use on the CO2 is not the same as emissions reduction. So that is a problem. And the other problem is that you must emit 25,000 tons of CO2 per year equivalent. And so not any industry can apply. Not every industry emits this much. The ones that I show you don't. Not even closer. Not even closer to the 20,000 tons. So how are we doing with the 2050 prediction? And I'm going to finish in 1 minute. I think this is my last slide. There are predictions. I think that we are a little bit far away from getting there. Incentives or opportunities for business might be the way to go. The International Energy Agency provides one view, and the IPCC, or the Intergovernmental Panel on Climate Change, provides another perspective, but it looks like there is hope in terms of that the millions of tons of CO2 on the vertical axis might become zero by year 2050. We will see. All this is happening and is forthcoming with some interesting ideas on the new industrial revolution, which is the Industry 4.0. There's some people talking about 5, but I think that this is 4.0. So we'll see more of this. Automation and all that is happening. More better qualified workforce is of the need, and particularly the new engineers of the future who are our students for sure. So with that, I would like to close, and I'll be happy to answer any questions if you have any. Thank you.
Thank you so much for sharing this important information about savings in the industrial management side, Dr. Cardenas. This is really cool. I don't see any questions either in the Q&A or in the chat. So
okay.
I guess before we go, can we just like move to the next slide? We would
Absolutely.
like to invite you to this technical course that we're offering. It's going to be in May 5 and May 6, 2026. Starting at 1 p.m. to 5 p.m. each day. It's going to be fully online in Teams. And we are going to cover some and going in depth in what of the topics that we covered today. For example, we're going to focus in practical skills to identify and quantify energy savings for boilers, HVAC systems, chillers, and compressed air systems. So this is a really good opportunity for the manufacturing facilities trying to reduce their energy use.
Yep.
Of course, the registration for this course is free until this Friday, so we encourage you to register if you want to be part of this one.
Absolutely.
It's going to be led by Dr. Cardenas as well, who is going to give a lot of details about the recommendations and everything.
Yeah, there's going to be a lot of secrets that you don't find in books. But anyway,
yeah.
But that's the idea, not to give you good ideas and think about new possibilities on how to think. And I give you one tip. If your energy cost is high, because in some states like Florida, the energy is deregulated, so you cannot buy from whoever you want. If the cost of energy is high, this is your opportunity to do energy efficiency. Why? Because you'll save more. And you save more because you're going to reduce some part of that. You will not pay any more. You put that money in your pocket, or you pass it into your clients and improve competitiveness. I'll leave it there. I hope that is of interest.
Yes, thank you, Dr. Cardenas.
My pleasure. Yes, thank you, Pablo.
Finally, the next slide, just like as we always mention, please, thank you for being with us. To the audience, you can scan the QR code and check our future events that we are planning to. So all the information is in there. And thank you for joining again. And we hope that you have a great rest of the day. Thank you, Dr. Cardenas, and thank you to the audience. Bye-bye.
My pleasure. Thank you. I hope to see you all real soon in those courses.